In this video, we'll continue to look at past paper questions for CSEC physics on atomic physics, nuclear physics, radioactivity, right? So in this video, we'll look at another past paper. This time we look at question 3 from, this is 2017, so May, June 2017, right? So question 3 from May, June 2017. Now, it says, explain elements with unstable nuclei are susceptible to decay. What is meant by the term nuclear fission? So what exactly is nuclear fission? So basically, nuclear fission is a splitting of a larger atom into two smaller atoms due to the absorption of a neutron, right? So usually, for instance, when an atom of, say, plutonium or uranium absorbs a neutron, it may split into two smaller atoms, and of course a few neutrons, typically 3 neutrons, are released in that process, and this is basically what nuclear fission is, right? So during the process of nuclear fission, when the uranium or the plutonium absorbs a neutron, it basically becomes very unstable to the point that it actually splits into two smaller atoms, and of course 3 neutrons are released in the process. These neutrons can actually go on to be absorbed or to be captured by for other plutonium or uranium atoms, and may result in what is called a chain reaction, right? Part 2 of the question says, state 2 advantages of utilizing nuclear energy. Now, we've examined this part of the question in previous questions. So basically, advantages of utilizing nuclear energy. Nuclear energy, it produces a vast amount of energy, especially when compared to, say, burning fossil fuels. So a small amount of radioactive, say, material will produce a much larger amount of energy than the equivalent amount of fossil fuel when burnt. Also, due to the fact that utilizing nuclear energy doesn't result in the production of, say, greenhouse gases like carbon dioxide, and it doesn't produce sulfur dioxide, which can actually result in acid rain, right? Workers in nuclear power plants need to be extra careful on the job. So this is part B of the question. Stage 1 precaution that workers in nuclear power plants need to take. I mean, even if you've never been inside a nuclear power plant, then of course you shouldn't have to think too hard about some of the precautions that must be taken by workers in power plants. Now, obviously, you wouldn't be in a nuclear power plant walking around in this attire, right? So workers in nuclear power plants must always ensure that they are wearing the proper protective equipment, right? Of course, in a nuclear power plant, they're always exposed to certain level of radiation, right? A certain level of radiation, of course, is deemed to be acceptable. So therefore, they must always be monitoring the level of radiation to ensure that everything is working okay, right? And of course, they must basically always abide by the safety regulations, so they don't really, risk exposing themselves to larger doses or amounts of radiation, right? Part 2 of B says, give 2 disadvantages of using nuclear reactors to generate energy. Again, we've examined this in previous questions. Disadvantages is that, the main disadvantage is that using nuclear reactors to generate energy results in a vast amount of toxic radioactive waste, and of course specialized facilities must be built to store this toxic nuclear waste, right? So basically, those are 2 of the disadvantages, right? Nuclear power plants are always designed with a very high degree of safety, but of course, we know that even if all the safety measures are basically put in place, there is always a potential of disaster, right? In 2011, of course, the Fukushima nuclear plant was damaged due to an earthquake, and of course persons in around the area were exposed to very high levels of radiation, right? Of course, further back there was Chernobyl, and of course there's always the risk of a disaster and the potential damage to life and the environment. All right, so continuing. So that was B, part 2 of question 3 from 2017. So part C, right, so part C, gives us a reaction. So uranium isotope, uranium-238, undergoes nuclear fission. Fission when struck by a neutron. Barium-139 and krypton-197 nuclei are emitted along with 3 neutrons as shown in the following equation. So let's just jot down the equation. So we have U-23892 absorbs a neutron and then splits into barium, mass number 139. We're given this letter P to determine that will represent the atomic number or the proton number of barium, plus krypton 9736, and of course we have 3 neutrons being released in the process, right? So this is basically the nuclear reaction equation where uranium-238 atom absorbs a neutron and then basically splits into 2 smaller atoms, barium and krypton, and of course 3 neutrons are released in the process, right? Now we're told to state the value of P. So in part 1 of that part, we want to state the value of P. Now during these reactions, we say that, as we mentioned in the previous question, mass must be conserved and charge, our proton number or atomic number, must be conserved as well. What exactly does that mean? It basically means that when we add up all the mass numbers on the left hand side, or the total mass of the reactants must be equal to the total mass of the products. And this is where we're talking about the atomic masses, or the mass numbers, which is basically large scale, right? So if we were to add up these numbers, say 238 plus 1, that gives us 239. So the total mass on the left hand side is 239. If we do the same on the right hand side, we have 139 plus 97. So this is 3 less than 100. So this gives us 236. Now we have 3 neutrons. So we have to multiply this by 3. So 236 plus 3, that gives us 239, right? So we see that the mass number is, of course, conserved. The same thing must occur with the proton number, right? So we basically say that the proton numbers must be conserved as well. And therefore, if we simply, so let's see, 2017. What am I looking for again? Right, so that mass and charge or proton numbers are conserved, and therefore we were to add up these numbers on the left hand side, they're supposed to be equal to the numbers on the right. So on the left we have 92 plus 0, so this is a neutron, it has no protons, no charge, and this must be equal to P plus 36 plus 0, right? So basically 92 will be equal to P plus 36, which means that P is equal to, what's that, 56, right? So therefore P is equal to 56, so therefore the atomic number or the proton number of barium is equal to 56, right? So we needed to have understood that atomic number must be conserved, and so therefore when you add up these numbers on the left hand side, the atomic numbers or the proton numbers, then they should be equal to the ones on the left as well. So this is 0, that is 0, so basically 92 would be equal to P plus 36, so therefore P is equal to 92 minus 36, which gives us 56, right? Good. That was that part 1 of the question there. So state the value of P. 2. State the meaning of C in Einstein's equation delta E. So they give us equation delta E is equal to delta M times C squared, right? So this represents the energy released during these reactions, right? Delta M would be the mass lost. Now mass is always lost during these reactions. Now once again, we say that mass numbers were conserved, but that is if we're talking about the atoms as a whole, right? The mass numbers. So the mass, total mass on the left will always add to get the total mass on the right. But if we're talking about in terms of atomic mass units, there's always going to be a slight reduction in mass, which of course is converted to energy, right? And that is represented by the delta M. Some books you may just see, without the delta, you may just see E equals mc squared, essentially as the same thing, right? So the question asks us, what does a C represent? The C, of course, represents the speed of light. So C is equal to the speed of light. Speed of light in a vacuum, which of course is 3.0 times 10 to the 8 meter per second, right? The next part of the question, part 3, says, calculate the total mass of the elements formed after the reaction, right? Now, there is a table which basically gives us the masses in kilograms. So we'll basically use those masses to find the total mass of the elements formed after the reaction. So having found the value of P, we can just replace the P with the number that we found. So this is 56. Right? So in terms of the total masses of the products formed, so we have barium, krypton, and the 3 neutrons, right? So for that question, let me see how many marks is, let me see. Calculate the total mass of the elements formed after the reaction. Well, the marks for that part isn't given, but for part 4, the total is 4 marks. Right, so the total mass of the elements formed after the reaction. Now, we're given the masses in terms of their respective masses in kilograms. Now, in this case, some students may actually think that they're supposed to add up the masses given here, whereas others may decide to use the masses given in the table, right? The question refers to the total mass of the elements formed after the reaction. So anyways, to be on the safe side, since it asks us to find the energy release in the reaction, to be on the safe side, we will actually use the masses given in the table, which are basically in kilograms, right? So in case of the barium, so the total mass of the elements formed after, so we can say total mass of the products, right? Let's call it total mass of the products. So this will be the mass of barium, which is given as 232.560 times 10 to the minus 27, but we can leave that off for a while. Krypton, which is 152.620. And then we have the 3 neutrons. The mass of 1 neutron is 1.670. So this is plus 3 times 1.670. And all of this, of course, is going to be multiplied by 10 to the minus 27 kilograms. Right? So when you work that out, what do we get? Two 232.56, 152.62. So that is supposed to give us 390.17 times 10 to the minus 27 kilograms, right? So that should give us the total mass of the products. All right, so after checking, this is actually 390.19. So 390.19. Right, times 10 to the minus 27 kilograms. Right? Now, so the total mass of the elements formed after the reaction is 390.19 times 10 to the minus 27 kilograms. Now, the next part of the question asks us to calculate the energy release in the reaction. Now, in order to calculate the energy release in the reaction, we first have to determine the total mass of the reactants, right? So total mass of reactants So this would be the mass of the uranium plus the mass of the neutron, right? And so this gives us 398.35 plus 1.67, and all of this is times 10 to the minus 27 kilograms, all right? So 398.35 plus 1.67, so that gives us 400.02. And in these questions, we try to keep all our decimal places, right? So 400.02 times 10 to the minus 27 kilograms. So we can see that basically there is going to be a slight reduction in the mass, as the total mass of the reactants is slightly greater than the total mass of the products, right? So we say the mass lost, M, is equal total mass of reactants minus the total mass of products, which gives us 400.02 minus 390.19, and of course all of that is times 10 to the minus 27 kilograms, right? What does this give us? Minus 390.19, that gives us 9.83. This is equal to 9.83 times 10 to the minus 27 kilograms. So the mass lost during this reaction is 9.83 times 10 to the minus 27 kilograms. Right? And so now we'll use our formula E equals mc squared to calculate the energy released. So we have E equals mc squared. Once again, m is the mass lost in kilograms. So this is equal to 9.83 times 10 to the minus 27 times the speed of light squared. So 3.0 times 10 to the 8 squared. And that gives us, this is times second function, well 1 second function exponential negative 27 equals. So times 3 second function exponential 8 times 3 second function exponential 8. And so this gives us 8.847 times 10 to the minus 10 joules. I guess the three significant figures, we could express it as 8.85. So 8.85 times 10 to the minus 10 joules. And this, of course, would be the energy given off due to this fission reaction, right? Now, in the last part of the question, they basically asked us to state one use of the energy release from the reaction. Well, I mean, we know that basically nuclear fission is used as a means of producing energy, which of course can be used to generate electricity, right? So in nuclear power plants, for instance, the energy which is released by this process is used to, say, for instance, boil some water, which produces steam, and the steam is then used to drive a turbine from which is used to basically generate electricity, right? So essentially, that is what the ultimate use of this energy is, to generate electricity, right? But directly, it may be used to boil water to produce steam to then drive a turbine from which you can actually generate electricity. All right, so that was question 3 from, what paper is this? May, June 2017.